Continue on talking about equilibrium of particles. A lot of times in a statics text, you'll encounter some very common types of devices. And we're going to talk throughout the semester types of devices. We're going to talk throughout the semester about different types of devices and the types of forces that they can or can't impart. But let's talk about ones that normally show up in an early chapter in a statics course, where we talk about equilibrium of particles, like what we're doing here. Commonly, you'll see things like ropes, cables, and chains. These can only hold tension. And what I mean by that is they can only pull. So if you see a rope or a chain or a cable applied to an object and you want to draw a free body diagram, replace on a free body diagram any rope, cable, or chain with a pull force. In the direction of, and I'm just going to write rope. It's the same for cable or chain also. So whatever direction it's pointing, you replace it with a pull force or a tension force. In 3 dimensions, that's where the idea of position vectors that we've talked about becomes so important. Is once you know what the position vector for that tension is, then you can just draw the x, y, and z components on your free body diagram according to those position vectors, or actually the unit vector constructed from those position vectors. Now, another subpoint here, ropes and cables are often considered weightless. What does that mean? That means tension is the same at all points. So if I have a continuous rope looping over maybe a pulley or through some sort of a system, the tension, no matter what it passes over or goes through, if it's the same cable or rope, it's the same tension at all points if we're considering it to be weightless. Chains may or may not be weightless. That's going to be left to what do you know about it in the problem description. If it has weight, you're going to have to know how long the chain is to figure out how much additional force is applied because of the weight. Those problems get a little more complicated. I normally kind of shy away from those types of problems myself when I'm assigning homework or putting test problems down, but that's just me. I can't speak. If you're not in my class, I can't speak for your professor, but that's normally what I'll do there. I've mentioned the term pulleys. Pulleys are frictionless unless otherwise specified. So we're going to go to the physics store, I like to say, and buy frictionless pulleys, because frictionless pulleys don't actually exist. They exist hypothetically in the physics store, but that's about it. However, what we're going to do is we're going to assume that the friction in those pulleys is significantly less than all the other forces at play. Same thing with cables and ropes. They're not technically weightless, but the amount of force applied to them normally is far outpaces or far it makes the weight insignificant compared to the other forces that are being applied. Same thing with the pulley. Normally, all the other forces applied to that pulley cause any friction going on inside the pulley to be insignificant. So, what does that mean? If I've got a rope or cable passing across a pulley, that means the tension is the same at all points in that cable because there's no friction in the pulley to change the force in that rope or cable. Another thing we might encounter, especially in an early chapter in a statics course, are springs. Springs are devices that apply a variable force as they stretch or compress. If you're hearing some snoring, it's Hazel. She's taking a nap. I apologize. So these are springs, and I will draw the most fancy spring that you can imagine. It'll look like this. Those are my springs. You do not have to draw fancy springs on my account. If you're a perfectionist, go for it. Make a much nicer looking spring. I normally try to focus on other things. The force applied by a spring is going to be proportional to what we call K and multiplied by S, which often that's going to be K times L minus L naught. And that is where K is essentially often referred to as the stiffness. And K is the stiffness, or sometimes called the Hooke's law constant. So Hooke was a physicist / engineer that ascertained that most materials will behave according to this, that if you stretch or compress them, they will apply a varying force, and it'll be linearly proportional to how stiff, if you will, that spring is. So the stiffer it is, the more force applied. S, of course, is often referred to as the displacement. S, of course, is the length minus the unstretched length. And L is current length. And L naught, or L0, is the unstretched length. So occasionally you'll see springs, especially in chapter 3. We probably won't see springs very often after that. So springs can hold, should mention, they can hold tension, which we've already mentioned is a pull, or compression. If a spring is in compression, that means it's going to apply a push force. Just barely don't have enough room to squeeze that in at the bottom there. Probably, if I'd have planned a little more ahead, I might could have. We'll do some real simple example work here. L4, page 5 of, and so if I've got, again, I draw my springs very simple. Let's say this is L naught, the unstretched length for this spring. If we compress it, something like this, so I apply some force to it, if you will. If I have something like this where it has been compressed, that is L, which is going to be less than L naught. this is going to apply a force. And of course that force is still going to be K times S. You're going to have a sign there, but the sign is really just telling you the direction of the force, if you will. But again, it can hold tension or compression. So if I've compressed the spring, if I've made it shorter, I've gone from L down to a smaller L, if I've made it shorter, it will apply a compressive force. On the other hand, or a push force. On the other hand, I'm sure you've probably, part of me wants to pull the spring out of this pen and show you. If you stretch the spring, where now I've got L is much greater than L naught, then it's going to, if I replace this on a free body diagram, it's now going to apply a tension force, a pulling force, which is still going to be K times S. By the way, if I'm in a hurry, I'll write more of a cursive K. I will interchange them. I will try to draw a block print K more often, but I make no promises. Okay. What do we got here? Let us do an example. Let's say that we've got ceiling of some kind. We've got some sort of a hanger up here and some sort of a hanger up here. And a cable actually this, so I've got a cable on, I had to look at my diagram there. I have a cable here on this side, and I actually have a spring on this side. I should have drawn that better, I apologize. So I have a cable on one side, and this is not a continuous line, this is just a spring on this side. If it wasn't already so many minutes in, I would just stop it and redraw it, but let's see what we can do. And then I'm going to hang from it a weight of 100 pounds. These are both at 45 degrees. These are both at 45 degrees. If the spring constant, the Hooke's law constant, the stiffness, if you will, is 100 pounds per inch, so spring constants will always be force per unit length, and the current length is 12 inches. We want to find the original length of the spring. So again, I've got a cable on this side, just some sort of a cable causing a tension force right here. We'll call this point A. Maybe we'll call this B, and we'll call this C. So I've got a cable running from A to B at a 45 degree angle. Then I've got a spring also at a 45 degree angle from A to C. The spring is currently at 12 inches. We have the spring constant there and 100 pounds. We want to find the original length of the spring. Okay. So what are we looking, so the procedure, standard problem solving says, what are you looking for? Well, you're looking for the original length of the spring, which means to find that, we mentioned earlier, this is what we know about springs, right? The force of the spring is equal to constant force of the spring is equal to the stiffness, the constant, times length minus L naught. So standard problem solving says, what are you looking for? We're looking for L naught. So what's a good tool to find, or what's a law or rule or good tool to find L naught? Well, the force of the spring contains L naught in it, so maybe that's a good place to start. And we say, all right, well, can we find everything else? I've got an equation here. Do I have as many equations as I have unknowns? Well, what's unknown? Well, I don't know L naught, and I don't know the force in the spring, but I do know the stiffness, the constant, if you will. Again, I'll try to not draw cursive K's. I saw you I had there. I am using cursive L's, but I do know the length. This is my current length of the spring. So I don't know the force, and I don't know the unstretched length, and that's what I'm looking for is L naught. So I've got one equation, two unknowns. I need to find, then, the force of the spring. So what's a good way to find the force of a spring? Well, if I can apply equilibrium to this knot, then I can probably find the force of the spring. So that means I need to draw a free body diagram of point A, the knot at point A. So if I do that, that's A. There we are, done. Now, what else do I need here? Well, I've got a tension from A to B. I'm going to draw it resolved. All right, so let's see, I've got 45 degrees here. So that means the tension's coming up here, and that means alternate interior angles are going to be congruent. This is 45 degrees there. So this is going to be, I'm just going to call it tension. You could call it tension AB if you like. It's just going to be tension times cosine 45 degrees. And then going up, I'm going to have tension sine 45 degrees. And then on this side, I've got force of the spring. And again, if this is 45 here, that means this is 45 there. So this is going to be Fs. This is going to be cosine 45 degrees. And then going up is going to be Fs sine 45 degrees. And then also applied to A, I've got one more force. I've got this 100-pound force going down. So I can write two equations here. It looks like I've got two unknowns is all. Sum of forces in the x direction. Fs cosine 45 in the positive, and the negative, so minus t cosine 45 degrees. That sum is going to be 0. One equation, two unknowns. All right, let's write another equation. You can write two equations per free body diagram. Sum of forces in the y direction. I've got Fs sine 45 plus t sine 45 minus 100 pounds. And that sum is 0. Two equations. Well, actually, I've got three equations. 1, 2, 3. 1, 2, 3 equations. I've got 1, 2, 3 unknowns. Solve. I will do everything I can when I grade problems to get you to at least 60%, if not closer to 80% of the points, if this is correct. If you'll do some algebra and try to get towards a solution, I can only get you to 80 points at this point. All right, so you're looking for L naught. Make sure that's clear, and then that means I've got to find Fs. Well, what do we know here? According to this equation, Fs is equal to T. By the way, if you want to pause, work through the algebra, find you an answer, and then come back, that's a really good way to do this. But I'm going to continue. According to this equation, because these are both cosine 45, Fs is equal to T. Okay? So with that in mind then, and again, I'm looking for Fs so I can find L naught is really what I'm after here. So with that in mind, that means this is Fs sine 45 plus T sine 45, so that means 2, because there's 2 of them. These Fs and T are the same. So it's 2 Fs sine 45. I'm going to move the 100 pounds over is equal to 100 pounds. Now what is Fs? I really don't care. Let me see if I've got it written down. I do actually have it. Right? So Fs then becomes, I have written here 70.7 pounds. If that's wrong, please feel free to tell me that in the comments. You can just solve for L naught and plug that in. Like you can solve this for Fs, plug that in here, solve for F naught or L naught, You don't ever actually have to find FS. But if you do, you can. And you should be able to solve then, given FS, plug that in here, you know K, you know L, solve for L naught. You should be able to find then L naught is 11.3 inches. And that's a 20-minute video, which is longer than I like to make them, so I'm going to stop there. But box in your answers or underline them for me, please.